All right, the second part to probability distributions is the two examples that I'm interested in. I did the first one showing a tree diagram, which we're familiar with from Unit 1, tabular, and a graph. So now moving on to something a little bit more challenging. In this one, we're looking at a dice game where we're rolling 2 die. The cost to play, so before you roll the dice, you have to put $7 in the pot. There's a winning chart down below provided here, showing all the possible outcomes. We want to answer the following. So the first one is we want to create a probability chart here. All right, so in order to create the probability chart, so we'll put A part right here. Our probability chart, what is the variable here? What are we interested in? Well, it's our winnings, right? It's our winnings. So we will put our money there. And then we are interested in our winnings, the probability of getting each value of winnings. So over here, this is going to be my small x. So I'm going to arrange them in numeric order, and I'm going to go smallest to largest, mainly because it's easier for me to follow along. So I see a 1, a 2, a 5, a 10, a 15, and a 20. And at this point, I just want to note, and off to the side here, this is all possible outcomes. All possible outcomes. There's no other money value that exists. All the possible outcomes are listed there, and it's very, very important with probability distributions. You list all the possible outcomes. Now, how do we find the probability of getting those values? Well, we're talking about rolling 2 dice, so important to use, if you have it handy, the dice chart. So I'll make a little bit of room here. I'm going to put the dice chart. I'll just shrink it a little bit so you can still see it. Okay. So the dice chart, very, very important in this case. So how many ways can I get $1? So if I'm looking at the $1, I had to have rolled a 7. And if we look at the dice chart, there are 6 ways to roll a 7. So a 6 in 36 chance for that to occur. To get a 2, I need to roll a 6 or an 8. So 1, 2, 3, 4, 5. 6, 7, 8, 9, 10. So there's 10 ways to win $2. The next one at $5 is a 5 and a 9. 1, 2, 3, 4, 5, 6, 7, 8. So an 8 in 36 chance. The $10, a 4 and a 10. 1, 2, 3, 4, 5, 6. So 6 in 36. And the $15 ones, we would need to roll a 3 or 11, which turns out to be a 4. And in order to win $20, it's either a 2 or a 12. Not only appears once on our chart, or sorry, once each, so a 2 in 36 chance. So on the left side here, we have all the possible outcomes, and that's what probability distribution is. All possible outcomes, and here's on this side, is all the possible outcome, the probability of each outcome occurring. So there is question A taken care of. Question B, determine the probability you win $5 or less. Okay, so for B part, how do you show this mathematically? So we know we are dealing with this notation here. Okay, that's the notation that we are moving to with probability distributions. So I want to know the probability that my random variable will be less than, and up here in B part it says you win $5 or less. So that means that it is less than or equal to our $5. All right. So that's less than or equal to. All right. How do we figure that out? Well, we look for the $5 or less, and we see that the probability of getting $5 or less, they're all listed here in the table. So we just got to add those 3 sums up, or those 3 probabilities up, to get our answer. So a 6 and 36, and this is why I don't, in this course, never reduce your fraction to the last step. Because now we just have to add the tops together, so we get 24 and 36. Which will reduce down to, they're both divisible by 4, so 6 and 9, or a 6, 9, or 2/3 of a chance. So there's a 2/3 of a chance that you're going to win $5 or less in this game. So therefore, or you can go to a percentage, 2/3 of a chance of winning 5 or less. That's dollars. All right, extend this down a bit further again. So C part, determine the probability you win at least $15. So what does at least mean? Probability that you win at least $15 would have to be greater than or equal to 15. So now you go back to your chart and find the values of 15 or greater. So there's only 2 here. There is only our 15 and 20. So we just got to add 436 and 236 together to answer that. So the tabular form actually turns out to be, once you get through it and get it set up, it seems it's helpful because you're just adding now out of that chart. So therefore, 1/6 of a chance to win 15 or more. All right, on to D part. Determine the expected value of each game when you play over an extended period of time. So what we're looking at is what can you expect to win here if you play this game for a long time. And long time is deemed as probably in this case you're looking at 36 trials or more. So expected value, and that's the formula I said we'd revisit and would make more sense to you once we went through it. So that's the formula there. So what it turns out to be, the expected value will equal, we take the first value, the 1, and we multiply it with its probability. So 1, oops, that's trying to make a fraction here. So 1 multiplied by 1 and 36, or sorry, 6 and 36, plus, and you move down the chart, 2 times 10 and 36, plus 5 times 8 and 36, plus 10 and 6 and 36. So all we're doing is we're multiplying the x values by their y values. Because it's probability, what it will end up doing is telling us over a long period of time what are our expected winnings. 20 and 236. So now you just need to go to your calculator. If you did it in percentages, it's fine, there's no problem with that. And your calculator will go through and calculate that for you. So we'll do that right now. So after using the calculator, I come out with, and because it's expected value for a monetary game, $6.28. So therefore, you would expect to win $6.28. Moving on then to E part, is the game fair? And F, what would be a fair price to play this game? I'm going to answer this both at the same time. So extend this down. So E and F. So is this a fair game to play? Some of you, hopefully most of you, are saying definitely not. And for those that don't see it, we'll talk about that right now. It's this answer right here of interest. Okay? You would expect to win 628. Well, hold on a second. To get into this game, for me to roll the dice, I had to pay $7. So if I have to pay $7 to roll, and over a long period of time, if I keep playing this game, I'm only going to make 628. Math would tell me that it's not a good thing. So this game is not fair. As it costs $7 to play, and I can expect to win 628. Now, this is what gambling's all about, right? The gambling is always beating the odds. You're never ever going to sit down in a casino game and it's in your favor. So, I mean, keep that in mind. But for this particular game, no, it's not fair because I'm going to lose money on on a long-term game process. So then F is what would be a fair price to play this game. To make this game truly fair, I would pay what I would expect to get out of it. So to make the game fair, I'll put that in quotation marks, fair, I should pay $6.28. That way, there's an equal chance of coming out even. So if you are lucky and you beat the odds, you may win $20 or $30, and that's when you'd quit. If you played it and you were unlucky and you made $1 or $2 back, you were losing money. However, if you were to continue playing the game long term in an ideal situation, in an ideal world, you would come out to break even in the end. All right. And again, when you go to Atlantic City or Vegas, anytime you sit down and see those casino games on TV even, it's always in favor of the house. The expected value to win is always lower than what you can expect to win, or the expected value to win is always lower than what you put into it. Okay? The only time you win at gambling is when you beat the odds or beat the probabilities. One quick example to finish this off, and I will finish that up in the next segment or the last segment.